Hello everyone. So today we're going to continue on 7.4. So last one we talked about was how to transform an XYZ coordinate system integral into a coordinate into an integral that uses spherical coordinate instead. And of course, this coordinate system, this type of change of variable would work perfectly if we try to deal with things that go in like a region of integration that's more spherical shape than a rectangular shape. So the formula is right here, which basically requires to do the same exact three things like we normally would do. Whatever regions we're given in XYZ, which is called region B, we have to kind of convert it into a new regions in D, which is in the spherical coordinate system r phi theta. And then we have to change the input of the function from xyz to become the transformation of r theta phi. So essentially basically meaning changing x, y, and z into the formula right here. Okay, and we replace dx dy dz with dr d phi d theta, but to do so we need to account for the ratio between these two set of differential, and for spherical coordinate system the ratio is r squared sine phi. So once again, we'll explain how that come about eventually when we get to the Jacobian theorem. So right now you just have to kind of trust me for this and just know that's what it is for your test. Okay. So what I would like to do is go over an example to show you how to use this. So example should be will be very easy. I'm just going to go and ask you to do this. Use the spherical coordinates system. Oops. To calculate the volume of a sphere with radius, how about just call it r? I mean, it could be a number, but I guess r is okay. So if you think about it, so this is how we define a sphere. Okay, a spheres in the x, y, z coordinates is basically something like this. Oops. Alright, there you go. Look pretty good. And it's defined by the equation x squared plus y squared plus z squared equal to r squared. Yeah, we write r squared too much. R squared. How do we form this volume? So I'm going to call this volume B. So therefore the volume attribute simple is given by this triple integral right here. There you go. So that will be the volume of B, which is the volume of a sphere's radius r. Plain and simple. But how do we evaluate this integral? So, well, I mean, we could evaluate using a regular xyz coordinates, which actually equal to this. The volume is actually equal to this integral. X from negative r to r. Integral y from negative radical r squared minus x squared to y equal to radical r squared minus x squared. And the integral z equal to negative radical r squared minus x squared minus y squared to z equal to radical r squared minus x squared minus y squared dz dy dx. So that would be an xyz coordinate integral that will allow you to evaluate the volume of this sphere. As you can tell, this is not an easy integral to evaluate, simply because whenever you have a square under the radical and a binomial or trinomial or a polynomial with square and under the radical, that make it extremely difficult to evaluate. Unless you go into some kind of trick substitution, it's very hard to evaluate integral like this. But lucky for us, we have something even better than trick substitution, and that is a spherical coordinate system. So I'm going to try to integrate this using spiritual coordinate system. So, but how? Well, actually quite simple. The first thing I need to be able to figure out is that what r phi theta that we can use to describe this entire sphere. So meaning what can I put into this transformation in the r phi theta space, which is also R3, but just using different coordinate system. And when I plug it through the transformation that we define for spiritual coordinate system, it will give me the entire sphere with radius r. Well, actually pretty simple. If you think about it, an entire sphere meaning that your phi has to rotate from 0 to pi. Because that would form a complete rotation from rotating straight up to straight down. Theta has to rotate all the way around. So 0 to 2 pi. R would have to go from 0 to capital R in order to form a sphere of radius r. So therefore, what we have is actually this. Guess what? The regions in r phi theta that describe entire sphere is actually a coordinate rectangle, where theta go from 0 to 2 pi, phi go from 0 to pi, and lowercase r go from 0 to capital R. So now I can simply just rewrite this integral into spiritual coordinate system, and I am just going to I'm going to just pick the order of integration to be dr, d phi, d theta, because that's how the coordinate appear. But remember, in our transformation, I have to put this in r squared sine phi to indicate the ratio between the two set of differential. I don't have to change the integrand because there's no integrand to change. Now I can set my limits. R will go from 0 to capital R. Phi would go from 0 to pi. And theta will go from 0 to 2 pi. So now comes the big question. Can I now evaluate this integral to get the volume of this sphere with radius r? And by the way, all of you should know what is the volume of a sphere with radius r going to be, because you know the volume formula for a sphere. And if you don't know that, you should. Okay? So now let's try to integrate this and see what happens. So that will be integral from theta from 0 to 2 pi, because I'm not dealing with this. And integral phi from 0 to pi, I'm not doing that either. Integral r squared sine phi dr is going to be 1/3 r to the third sine phi. Evaluate from r equal to 0 to r equal to capital R. D phi d theta. And remember, capital R represents a constant, not a variable. So when I plug in 0, r to the third will be 0, so that's gone. When I plug in capital R, I just simply rewrite the lowercase r to capital R, so that's it. So that would mean that this is my second integration. So now if I integrate that with sine phi d theta, d phi, that would be theta from 0 to 2 pi. Oops. And this integral become 1/3 r to the third. The integral of sine phi is cosine phi. But cosine the negative. Evaluate from phi equal to 0 to pi. So, d theta. So if I plug in 0, I'll plug in pi first. Actually, if I plug in pi, cosine pi is actually -1. So therefore become 1/3 r to the third minus. If I plug in 0 for cos into phi, that would be cosine of 0, which is +1. So become minus 1/3 r to the third d theta. So that just happened to be 2/3 r to the third d theta. And when I integrate that with d theta, since that have no theta in it, I'm going to just treat the whole thing as a constant. So become 2/3 r to the third theta. Theta from 0 to 2 pi. So plug in 0, go to 0. Plug in 2 pi, I'll get 4 pi over 3 r to the third, or 4 pi r to the third over 3. Okay, actually, maybe I'll write it this way, because that's probably how you remember. 4/3 pi capital R to the third. Ugh. Yeah, it's so automatic when I write the word R, I draw that second line. There you go. Which you know for a fact that that is the volume formula for a sphere. And notice that this integral cannot be done, but once you change it into a spherical coordinate system, this irregular shape turn into a nice coordinate rectangle in a rectangular coordinate system, which makes it a lot easier to evaluate. So, oh, by the way, this region is probably I would call D. That corresponding to B. Alright, the next thing I want to talk to you about is this one. It's the last coordinate system, which is our cylindrical coordinate system. Alright, so I'm going to try to follow the same structure. So I think the first thing I'm going to show you is what this coordinate system does. So here's the transformation. Oops, let me see. Okay. Okay. Just try to see what I was doing before so I can do the same thing. So here our cylindrical coordinate system will be the following. Let t, that map u3 to r3, and t of r theta z is equal to r cosine theta, r sine theta, and z, which is just x, y, z. Okay, so in here, if you remember, look back at your notes. We talk about in 6.5, r would go from 0 to infinity, theta would go from 0 to 2 pi, and z would actually go from negative infinity to positive infinity, because that just moves straight up and down. So here's a definition of how to transform using a spherical coordinate system. So I'm going to say definition. So I'm going to kind of list it the same way. We're going to start with regions B. Let B be a region in R3 using the X, Y, Z coordinate system. And let's say we have T of R theta Z be the cylindrical coordinate transformation. And of course, we need a corresponding region to D to B, which I will call D. Let D be the region in R3 using cylindrical coordinate system. Such that T of D equal to B. So now I'm ready to show you what's the formula that we can use to rewrite this coordinate. So once again, let me draw this picture. So therefore, we talk about D in the R theta Z space. After transformation, it will turn into, in the XYZ space, what B will look like. Okay, so if you want to picture, that's basically this picture right here. So this is D. Once I put in through transformation, it actually turn into this thing, a sphere. So that's why it's called transformation. So what is the formula in this case? So a triple integral Riemann of B in the XYZ coordinate system with D. Let's see what I wrote. I think I just write dy dx. Yeah, dx dy dz. So dx dy dz. So remember, this is, technically speaking, is basically what dv in the xyz coordinate system look like. It would equal to a triple integral over d f of t of r theta z. So that's the same with formula composition that will account for how to change the integrand into a new coordinate system. We replace the region of integration with d. So now comes the interesting thing. What is the correct way to change the differential? And that will actually be this. And does that seem shocking to you? You have seen this before, but it shouldn't be, because in this case, our dv of r theta z and xyz are only different in r theta replacing x and y, and therefore imply that that is just simply the polar coordinate transformation. And therefore, if you look at our rule for polar, dx dy is actually just equal to r dr d theta. So dx dy dz should equal to r dr d theta dz. And that's exactly how that works. So note, dx dy dz is actually equal to r dr d theta dz. I'm going to highlight the r. There you go. So that you know, that's important. So notice that would mean that using the cylindrical coordinate system is almost as easy as using the polar coordinates, which is one of the reasons why we really like using cylindrical versus spherical, because the spherical is just a lot harder to do. Now, obviously we're going to have to try a problem together. So let's go and give this problem a try. Let's say, here's our question. Let's say B, let B be a region in R3 that is bounded by the following inequality. 1 is less than or equal to z, which is less than or equal to 4. X squared plus y squared is less than 4, and 0 is less than y, which is less than x. And let's say we have a mu of xyz equal to x squared plus y squared plus z squared be the density function for regions B. We want to try to find the mass of B. So let's try to take a minute to think about what this looked like, okay? So let's see if we can figure this out. So I'm going to, once again, this is the kind of problem that I have a perfect mental image in my head. I just don't know how that's going to come out when I draw it. So let's find out. So here's my z-axis, x-axis, y-axis. Here you go. Here's x, here's y, here's z. Okay, so let's try to draw this out. So z between 1 and 4, basically meaning that we have basically two planes. One plane is z equal to 4, and then one plane is on the bottom, which is z equal to 1. Okay. Alright, it's fine. I'm going to leave it. X squared plus y squared less than 4. You might be thinking, doesn't that form a circle? No. It does form a circle in R2, but it doesn't form a circle in R3. So what does it actually form in R3? We actually form this. So I'm going to actually I want to actually move this so that I have more room to draw this. There you go. It actually form a columns that go on forever. So of course it will intercept the two plane in a circle. And therefore the part that in between these two planes will actually be that like little cylinder right in between those two planes inside. And now what is x is greater than y, which is greater than 0? What does that do? So that would mean that we actually have the line y equal to, let's see if I use a third color, y equal to x and y equal to 0 right here. And what everything get between these two things? So what's the implication? It would actually form this part right here. So now I'm going once again. This is what I visualize in my head. I'm hoping that the picture will look nice. So it would be something like this. Alright. So if I pull that picture out, it will actually form something like this. Alright, something like this. So the best way I can describe it is, it's like a slice of a cake. Yes. Okay. So this plane right here is basically y equal to x. And then this line right here is y equal to 0. This kind of curve right here is x squared plus y squared equal to 4. And then the top is basically as z equal to 4. And then the bottom is z equal to 1. So how do you calculate the mass of this thing? Well, simple. So we're going to call this b. So the mass of this thing is just a triple integral over b. X squared plus y squared plus z squared dv. So that's easy. How do you evaluate that? So evaluating that would be a lot harder, and I'm not going to attempt to try to set up a Riemann integral, a triple Riemann integral for this using this picture, because that would require me to split this into at least 2 different pieces of solid. So I'm not going to try to do that, but instead I'm going to try to describe this in using a cylindrical coordinate system. So how does that work? So what would this regions look like in r theta z? So let's find out. So what we're trying to do is try to figure out, after transformation, what should this solid look like in the r theta z space. Okay, so let's try to figure this out. So first thing I notice is that the z actually stays the same, so therefore we go from 1 to 4. So that's pretty easy. The radius is 2, this solid, because x squared plus y squared equal to 4, so radius 2, so therefore the radius actually go from 0 to 2. So let's say here's 2. That's 0. The tricky part is what should theta be? So if you think about it, y equal to x is actually the diagonal that split the first quadrant into 2. That is actually 45 degrees or pi over 4. And then theta would go all the way from pi over 4 to the y-axis, which is actually pi over 2. So there you go, there you have it. This is the solid that we have. So I'm trying to draw a dotted line to help me kind of visually see how these work out. And so here's my regions. Yeah, let's use red. And once again, I'm going to need to trick your brain into thinking that this thing pop outward. So I'm going to draw the dotted line in the back. There you go. Guess what? It's formed a nice rectangular, coordinate rectangle in r, theta, z space. One of the nicest thing is because what we're talking is a piece of a cylinder, therefore it's going to be perfectly described using cylindrical coordinate system. So now I'm going to set up this integral. So this mass is actually going to equal to the triple iterated integral. Z would go from 1 to 4, so I'm going to do dz last. I guess I just go in order dr, d theta, dz. So theta would be the middle. That would go from pi over 4 to pi over 2. And then r would go from 0 to 2. And our integrand will be x squared, which is r cosine theta squared, plus r sine theta square plus z square dr d theta dz. So let's see if we can quickly evaluate this integral. So hopefully you have seen this before. This part right here, just become r square times cosine square theta plus sine square theta. So that just become r square. So therefore my triple integral is z from 1 to 4. Theta from pi over 4 to pi over 2. R go from 0 to 2. R squared plus z squared dr d theta dz. So the first integration is dr. So therefore it will be 1/3 r to the third plus z squared r. Or rc squared, actually maybe I'll write it better. Rc squared, evaluate from r equal to 0 to 2 d theta dz. So when I plug in 0, both of these go away. Plug in 2, give me 8 over 3 plus 2z squared. So if I integrate that with theta, that just actually equal to this. 8 over 3 theta plus 2 theta z squared. Theta from pi over 4 to pi over 2 dz. So now when I plug in pi over 2 and pi over 4, I should have 8/3 times pi over 2, so therefore become 4 pi over 3 plus pi z squared minus, when I plug in pi over 4, it becomes 2 pi pi over 3 plus pi over 2z squared. So if I combine them together, 4 pi over 3 minus 2 pi over 3 become 2 pi over 3. I have pi z squared minus pi over 2 z squared. So that become plus 3 over 2, 3 pi over 2, actually just pi over 2 z squared, dz. And now I'm ready to integrate from 1 to 4. So if I integrate this, that becomes 2 pi over 3z plus pi over 6z to the third from z equal to 1 to 4. So if I put in 4, I get 2 pi over 3 times 4, which is 8 pi over 3, plus 4 to the third over 2 over 6 would basically be 32 over 3 pi, minus, when I plug in 1, this is 2 pi over 3 minus pi over 6. So let me see. So if I'm looking at this correctly, that would be 16 pi plus 64 pi minus 2 pi minus 4 pi minus pi over 6. So look like 75 pi over 6. So if I divide both by 3, 75 pi over 6 is 25 pi over 2. So hopefully I did my math correctly. Let me just quickly take a look. Yes, 76 minus 1 is 75 over 6. So that seems okay. Alright, so that's my answer. That is the math. Alright, today's video already passed 32 minutes, so I think I will stop right here. So tomorrow, or actually next video, we actually go talk about Jacobi theorems, and that way we can finally explain. I can finally explain to you where those weird values that correspond to the different differential come from. Alright, so I'll talk to you again in the next video. Okay, bye bye.